Testing web apps is very, very easy, said no one ever. And the reason we are not saying this as often as possible is because the browser experience has evolved. We're no longer making blog posts, links, articles, a very static experience, and we have now moved to the amazing web that we have today. To give you an example, the James Webb Space Telescope that brought to us never before seen images of the universe is running JavaScript. The SpaceX Crew spaceship that takes astronauts from Earth and takes them to the International Space Station is also using Chromium and JavaScript for their touchscreen UI. So the web has evolved from being a very static place to being so dynamic, and testing has to evolve alongside with it. We now cannot afford to have things go wrong to us in production because either companies are losing millions of dollars or we can endanger human lives. So before we begin, let me tell you a story. I work as a software engineer at Glovo. We are a food delivery company. It was founded 8 years ago in Barcelona, and it operates in close to 25 countries. Tech-wise, we have a lot of applications. We have app for couriers, for partners. These are our stores. We have an admin, and we have customer applications. In total, we have 500 engineers working on these products, and I think we have passed the 100 microservice limit. We have apps for the customer applications. We have iOS apps, Android, and web. All three of them use the same API. And together, they bring in 20 million monthly orders. And we reach around 30, 35, or 40 million users every month. And like I said, we have 500 engineers in our company. But what makes Glovo unique, at least for me, is that we have absolutely no quality assurance hired. So we have no QA. And for me, in my previous companies, I used to have in my team at least 1, 2, even 3 QA that were doing automated tests, API tests, manually testing your application, and moving from that sort of company to where I have 0 QA in the entire company was a very new experience. And in the onboarding process, I've asked my buddy, hey, how are we doing things here in this company? How can we make sure that we're not breaking production? And what I received in response was, you have to follow the old school testing pyramid. So you have to, for each new features, you have to write a lot of unit tests, write a couple of integration tests, and if your feature is considered business critical, you may write an end-to-end test to cover the flow. And after you've done all of this, you boot up the project and manually test your feature. And I was like, manually test my feature? This isn't something that we developers usually do. We're lazy. We don't have that attention to detail that we usually practice. But I was at the beginning of my journey, and I wasn't going to ruffle any feathers. So I did what I was told. So I had a feature that was supposed to change something in the sign-up dialog of the application. And I finished it. I wrote some unit tests. I wrote a couple of integration tests. At the end, I wrote an end-to-end test to cover this new flow. Of course, I manually tested my feature. And in response, what happened was I broke the CSS of almost all the dialogues in the application, all of them. Well, I say almost because I didn't break one, the one that I was working on. So that was, for me, a very good job done. A funny thing is that this was happening 2 years ago. We didn't have continuous integration, and we were doing releases every 2 weeks. And the release commander didn't consider breaking the CSS of the entire application of the dialogues as critical to revert 2 weeks worth of code. And I had for 2 weeks to keep this in production. Everybody was laughing at me. I had to not look people in the eye when I walked past them. It was a wonderful experience. I was expecting my manager to hit me up on Slack and say, get out of here, you're fired. But thankfully, that didn't happen. But we learned a critical thing is that the testing pyramid, the old testing pyramid, was not working because it was relying on outdated metrics. It was comparing speed. The response was that unit tests are faster to run than end-to-end tests, so you should write more unit tests. It was comparing costs. It was saying, hey, developers take less time writing unit tests than they do end-to-end tests. So again, let's write more. And it was not comparing confidence. Even if your end-to-end, your unit tests were passing, you didn't feel that confident in your feature. You still were a little scared when it reached production. Instead, if your end-to-end tests were passing, you were absolutely confident that you at least won't break any business critical flow and not lose any money. And of course, there are other testing structures out there. There's the testing cup, which is pretty famous, the testing obelisk, where it's basically the testing pyramid with extra layers. And I could have used one of these for this talks, but I've decided to, make my own testing structure so I can put my point across more clearly. So I invented the testing wormhole. And besides the fact that it's way, way cooler than a testing cup or a testing pyramid, it also has the benefit of being in space. And if you know, in space, nobody can hear you scream your frustrations that your testing are not passing. There's also no left, no right, no up, no down in tests, so there's no pillar that brings up the entire pyramid. Every part of the testing is as important as the other. So for today, I'm going to talk about 3 pillars of the testing wormhole: lazy tests, unit tests on steroids, and feature tests for the front end. And when I say lazy tests, I mean tests that you usually code it and forget about it. You don't have to maintain them. You don't participate actively in every PR or feature that you write. You wrote it in the beginning of the project, and you forget about it, and you don't touch them again, only when you need to update to add extra rules. So basically, they're like the static checks that you need in a project. And how we do this, usually, is you have to automate your commits. So we're using a third-party library called Husky, which generally allows you when you have, before you publish a commit message, it runs whatever scripts you declare it in your package JSON. So for us, a typical example is to run our linter rules. So we want to make sure that everybody in the company is following the same coding standards. We want to check for typos to see that there's no typos in our code when we push a PR. We have all sets of rules, like we want to enforce better accessibility practices. We want to make sure you're not importing components directly. We want components to be part of a module, and in that way, we enforce the modularization of the application. And in the future, if we want to move to micro frontends, that's fine. We already have that modularization in place enforced by these rules. And another type of lazy test that I'm going to talk about is performance tests. Now, I'm not going to go into detail about performance. You can fill an entire conference talking about it. But the main 3 pillars as defined by Google are LCP, FID, and CLS. And there's a clear correlation between having a better performance and increased CVR, conversion rate. And there's articles written about this, there's research done, but it makes sense. Like if the app boots faster, the user is going to interact with it faster and probably going to order faster than an app that is slow. And performance testing, you can measure it using Lighthouse, web page test, Google Search Console, the Google Crux report. You can have in place observability tools like Datadog, Sentry. We found that for us, web page test and Google Search Console brings us the better results. What we do is Google Search Console groups your URLs, and it tells you, hey, your LCP is larger than 4 seconds for this group of URLs. And you take one, you go in webpagetest.org, and you zoom in on the problem and see how you can improve it. And this is fine for testing and doing it yourself for each PR, but we want to have limits in place that prevents other developers from breaking your production website for increasing the performance. So we have Lighthouse that you use in a browser, but it's not scalable for each developer to check Lighthouse over and over again. It also is very dependent on the speed on your machine. So as we usually use MacBooks, the performance is going to be, it's better on my machine than someone using Android phone somewhere in Africa. So we have CI, we use Lighthouse CI to automate this in the CI build. Lighthouse has different versions of documentation depending on how knowledgeable you are about CI practices, how knowledgeable you are about performance, but it helps you do the basic thing. And usually coding performance test is very, very simple. What happens is you basically care only about one command, and that is ci.lighthouse. You pass in some thresholds, and you pass them some options, and for each page you pass, it's gonna boot up a browser. This is what the pipeline does. It boots up the browser, and it runs the metrics multiple times, and it takes an average. And if that average is above your threshold, it's going to break the CI pipeline, and your pull request will not go through. This way, we keep performance at constant levels. Another thing that we found out that if you are using, of course, a lot of frameworks, JavaScript frameworks, it usually is going to bundle up your JavaScript into one file. And we found out that if this file is bigger, of course, performance is going to be slower. So we want to have rules in place that prevent other developers from majorly increasing the bundle size. And we're using, again, a third-party library called BundleLemon. This is a wrapper upon a much more popular library called Bundle Size. And here we can set up limits to the bundle. So if we want to say, please don't go over 200 kilo, it will break the PRs that are trying to go afterward. And why we're using another wrapper about bundle size is because it also comes with an ability to limit max percentage, not just the hard limit. So if one PR is trying to increase, it doesn't reach the hard limit, but it increases over the 2% that we want, again, we're going to break the pipeline and say, no, try not to add this much code. Find a way to improve it. So in conclusion for this part, keep your bundle size, use linter rules to enforce best practices. An increase in performance can significantly affect conversion rate. Use Google Search Console, the Crux report, and everything Google has to offer for performance so your CEO ranking is good. And use RUM tools and observability to measure everything. Now that we've talked about the code that you write only in the beginning of the project, in the middle, we're going to talk about the code that you usually write the most, and that's unit tests. And unit tests are the pillar of the old school, the first level of the old school pyramid. You were supposed to write millions and millions of unit tests. That's what the lectures are telling you. And a unit test is basically testing the smallest unit of code. So you have a pure function. It takes in some parameters. It does some magic calculation, and it outputs a result. So for example, a sum function takes A and B, returns the sum of these two. A normal unit test would import the sum function, pass it 1 and 1, and expect the result to equal 2. Now you may go a little bit further and try some different parameters. You will say, hey, let's try negative numbers and see that the result is, as expected, -2. So you're testing boundary situations. Then you might go a step further and test what happens if instead of numbers, I'm passing strings. And then you would expect normally to have an error or the result, depending on your situation, to be whatever you need. And this is very fine and good practice, but for pure functions, utility functions, helpers, and mutations, API responses, but 90% of our applications are not pure functions. They're actually components. So usually we have something like this. This is a typical tutorial component. It's a counter. It has 2 buttons, a plus and a minus, a heading where you see the result of the counter. And then you have the logic of the component, where you set the default values, what the functions are doing when you click the buttons, and basically that is it. So this is a normal component. And when you will try to unit test this, what would you first think of doing? And before unit testing, you have to look at your component code and ask, does this part actually need to be connected to the document in any way? Or can we remove parts of this code and test it in isolation? Because that's what we want. We want unit tests to be small. We don't want to mock everything in this function to do. We want to test very small units of code. So thinking about our increase count function, we can very easily extract it instead of mutating the state. It could be in a separate helper function, where it takes a value, depending on the situation, it might increase it or not, and returns the value back. And this you can import it in your unit test and very easily test it. You can test what happens if you have 0 and you want to increment by 1, what happens if you have a 10 value and you want to increment by 1, and so forth. And this might be great. You start writing a lot of unit tests. You probably have tens and thousands of unit tests. But if you come into a project with so many unit tests, you don't actually know how many of them are doing their job. Maybe they are throwing false positives. So who is watching the watchers? To give an example, our sum function, instead of returning the sum a plus b, by mistake a developer makes, it returns the value 2. And then your unit test is testing for the value 2. Of course, the terminal is going to say, hey, good job, all is green, but this is actually a false positive. And it's typical for unit tests if you mistakenly remove the expect statement or put the expect statement into an async function, you may skip it completely and the test is green. You're not actually testing anything, so you're going to have a lot of false positives in your code. And to solve this, one solution, of course, is to have mutation testing in place. And mutation testing, the goal for them is to bring a little bit of chaos into your code. What happens if, what mutation testing does is it takes your code and modifies it just a little bit. And instead of having your sum function, a pure function that has input, calculation, and output, it modifies the magic calculation just a little bit until you have your code is a little different. And then it runs the unit tests. And if the unit tests fail, that means your unit tests are good and the mutation is killed. But if the unit tests pass with that modification in your code, that means you're having false positives and the mutation is kept alive. And it goes further. It modifies it a little bit more, until the code is unrecognizable. And if your unit tests continue to pass, you still you have those mutations at the end, and you can debug and see where your unit tests are flaky and are bringing false positives. And this is, like I said before, you can do them asynchronous. You don't have to have mutation tests in your CI pipeline. You can do them, run them once a month or once a quarter, and decide if your code is, your unit tests are doing as they expect. A proper example is our sum function that takes a, b, and returns the sum. You're expecting the result to equal 2, and then you just modify the plus and create a mutation. This will run the test will fail, and the mutation will be killed. So in conclusion, apply these practices to increase confidence in your tests. Mutations, like I said, can be asynchronous. Separate logic from UI. Please test results and not implementation details. Keep the test compact and readable because they provide a very good documentation. Like it was said before, developers don't really like writing documentation, so take advantage of unit tests. And if it's difficult to set up, you have to mock all sorts of third-party libraries. Maybe a unit test is not the perfect job for that component, and try a different method of testing. And even if you have all sorts of unit tests and you have millions of them and your feature is so well unit tested, that does not mean that your code is actually behaving like a user expects. you're basically testing functions here and there, while the actual user may interact with it completely different. So before we go to the last part, we need to think about having feature tests in place that actually test like a real user. And this usually is the top level of the old school pyramid: integration tests, system tests, end-to-end. And I'm going to start with visual testing. Visual testing are very simple to write, exactly like performance tests. You just need basically one command, set up the test and say, hey, go to this page and check it for errors. And that's it. Before you would have 10, 12, 13, 14 rows of code. Now you just have one. And what visual tests are doing is they're taking a picture of the master branch, what you have in production, and comparing it with your PR. And then it spots the difference. It does image comparisons, and it spots the differences, and it's going to tell you. The reason this is not a lazy test, and you actually have to continuously improve it, because usually visually your application changes a lot. So every time you don't have to change the code you've written, but you have to go and say thumbs up or thumbs down to the library that you're using if this change is actually breaking or it's an actual good change that you want to introduce. So this is what it does. It compares images. It's going to tell you afterward the result. So for example, you see here that some icons are missing, some text is different, and it's going to alert you of these changes. And you're going to say it's intentional or not. And if it's not intentional, it's going to stop the PR from merging. And you can go a little bit deeper, hover over elements, see what's is wrong, and make the decision for yourself. And now, once you have all of these in place, visual tests for each page that you visit, usually you look at the highest traffic of pages, you group those URLs into your routing components, and test just those pages. And once you have this in place, new joiners won't be breaking dialogues in your app anymore. You're going to have clear limits for your CSS. But the one problem with visual tests is that you can't actually test interactivity. You cannot test what happens when you scroll, what happens when you're clicking buttons. You can do it, you can force the library to do these sorts of things, but usually you introduce flakiness. So a better approach is to have component testing for your components. And going back to the counter button that we talked about before, we have the setup in the beginning, the increase count, the decrease count, and then the buttons and the result. What we should be focused on is obviously the result. We don't want to test implementation. We want to just see that the heading is showing what it's supposed to when you click the buttons. So you have, what component testing does is it boots a browser and just takes your component and starts a single page application app with that component. So it doesn't care about the rest of your application, it cares just about that component. And you can interact with the elements in your component using area labels, using CSS, using IDs. So basically what a user is seeing. You can say, hey, get that button that has the text add, and just like a user would see it, you would get that button. You can mount the component with props or with extra props, with whatever you want, and test different scenarios. And of course, you can test the buttons that they're working. You mount the component, you get the button, and then you click on it. And you see that the result, this is what we care about, is what we want to have. So in conclusion, using a real browser is necessary to test real components. Before, you would use a terminal if you wanted to do like integration tests, and you wouldn't actually know what's happening, what's really happening behind the scenes. Using a real browser, you can see exactly what is being rendered and what your user is seeing. And this is also good for the development environment. You don't have to boot up the entire application while you're coding. You can just boot up this component and see just what you're working on, and your laptop is going to be happier because it doesn't have to take out that extra energy that booting an entire application would cost. And of course, testing like a real user, that's the best conclusion that I can wrap up. And speaking about real users, I'm going to end the talk talking about, the more controversial topic and the solution we took to it. So this is end-to-end testing, of course. End-to-end testing for your features usually follows a user's journey from the beginning to the end. Usually, like in an e-commerce website, it would be like from the beginning of the homepage, you go to the catalog, you reach the product page, you put your products in the cart, and then you reach checkout and you pay. This is a typical user journey that you want to make sure in production is working correctly. And if you have worked with end-to-end tests before, you know that typically you encounter the same problems. They are slow. You have to wait for the API responses. They are very flaky because the API might change. You don't have that much control over it. And you're writing a lot of duplicate tests. So every time you're writing a user journey, in the middle, you may encounter the same segment. So you're retesting that segment again and again and again. So now what we decided at Glovo to do, which is a little controversial, is to mock everything. So we decided to mock the API, have contract testing in place, so when the API changes, the production does not break. We're running our end-to-end tests in parallel to make sure they're no longer slow, and we've implemented skip functionalities into our code to make sure we're not retesting the same segment over and over again. So mocking the API, we created in our application a mock server that we set up when the end-to-end tests are running. And this mock server is a proxy to the real application, the real backend. And when you run it once, it records the production results, and it saves that result as JSON files. So you have all these JSON files that you're receiving very, very fast from inside your own application. So you don't care that the API is down, that staging is down, that production is down, or anything else. Your pipeline is on block all the times because you're using the same API that is local. Of course, this is not ideal. We are serving JSON files, so it's very, very fast. And for a server-side rendered application, it happened to us that the browser was rendering so fast that the hydration was not happening. And Cypress was trying to click the buttons, but there were no event handlers attached to them. And the tests were failing. And we had to work around it a little bit, create some custom functions, slow down the response intentionally to simulate a real response. And what we also put in place to make sure that the API is not changing is contract testing. And contract testing for us, the front-end application, are a consumer. And we declare to a third-party library, hey, we're using these endpoints, this, and this, and inside we want this flag to be true, we want this flag this parameter to be a string, we want this to be an array, and this gets published, and for every PR the backend is trying to merge, it checks the response that we're expecting as a consumer to the response they're outputting. And if there's any change to it, the backend PR is going to fail. Using Cypress orchestration parallelization orchestrator, we're parallelizing all our end-to-end tests and breaking them up not only just by spec file, but by every describe statement that we have. And that way we run all our end-to-end tests in parallel. To visualize how this is happening, we're not waiting for all of them to complete. If you have a failure, the Cypress orchestrator is going to skip the remaining end-to-end tests. So you get the feedback loop as soon as possible. You're not waiting for extra resources to finish. And talking about the skip functionality, like I said before, if you're in the home page and you need to reach the catalog, you may need to add an address. You may need to log in to check the checkout. So these functionalities, the add address, the login, are always being tested and retested in all of your test cases. And you don't want to waste those precious 10, 12, 20 seconds, depending on the case, retesting everything again. If it worked once, probably it's going to work every time. Of course, you're going to have a test in place to test this alone, but you want to maybe skip them for the rest of your unit, your end-to-end tests. And how we do this is, in your development environment, we have flags in the URL, and we specify, hey, user logged in equals true. That means we bypass that flow entirely. Or we take advantage of cookies, and we boot up Cypress or Playwright or whatever library we're using to simulate a logged-in user, or a user with an address, or a user who does not need to go through all of these steps. So in conclusion, CSS and design matter. Have checks in place like visual tests, so new joiners will not be breaking the app anymore. Use component testing like a user in a real browser. Test results and not implementation. End-to-end tests are flaky, but they give you the most confidence in your code that you're not going to be costing the company money. Don't duplicate tests for general functionality like login, and parallelize your tests in your CI/CD pipeline. Our test parallelized now run more fast than our unit tests, which are also parallelized, but we have to group them. Testing web apps is easy. I hope in the end some of you may feel that way after this talk. Ευχαριστώ.